We know that we can estimate functions using Taylor polynomials. We also know that those Taylor polynomials get more and more precise as we add on more and more terms. Here, we're going to examine how much error we might find in any given Taylor polynomial. As a reminder, the nth order Taylor polynomial, which approximates a function f of x centered at a value x equals a, is given by the formula the sum from k equals 0 to n of the kth derivative of f at a divided by k factorial times x minus a to the k power. To help us understand the error in a Taylor polynomial, let's look at this animation. Here we have the first order Taylor polynomial approximation of the sine function. The orange bar in the animation is the error, the difference between the value that the polynomial, the green line, gives us, and the actual value, the sine function, indicated by the blue graph, gives us. As we watch the animation, a few things become clear. First, we can see that the error depends on the x value. As we move along the x-axis, we can see the error shrink as we move towards 0 and grow again as we move away from 0. The other thing we can see is that the error gets smaller the closer we are to the center of our Taylor polynomial. In this case, we're centered at 0. Because we know that the error is a function of x, that means that we can rewrite our original function f of x as the sum of the nth Taylor polynomial plus a new function r sub n of x, which represents our remainder, or the error, in our Taylor polynomial. It turns out that Taylor discovered a useful and wonderful formula that gives us a precise value for that remainder. Taylor's theorem tells us that r sub n of x, the remainder in the nth Taylor approximation for a function f of x, is exactly equal to the n plus first derivative of f of c over n plus 1 factorial times x minus a to the n plus first, where c is some number that falls between our x value and a, which is the center of our Taylor polynomial. The tricky part in this formula is that we don't know which value to pick for c. However, if we can find a maximum value for the n plus first derivative for all values of c between x and a, then we can find an upper bound for our remainder. This idea leads us to Taylor's inequality. If we know that the absolute value of the n plus first derivative is less than or equal to some number m for all c between our given x and the center of our Taylor polynomial, then we know that the absolute value of our remainder is less than or equal to m times the absolute value of x minus a to the n plus first, all over n plus 1 factorial. We saw earlier that the linear approximation, the first order Taylor polynomial approximation for the sine function, provided a fairly reasonable estimate for that function for values that were close to 0. So let's use that to estimate the sine of pi over 16 using a first order Taylor polynomial, and then let's use our error bound to find an upper bound for the error in that estimate. First, let's construct our polynomial. We know that p1 of x is going to be equal to f of a plus f prime of a times x minus a. Our f of x is the sine function, and our a value, we're centering this at 0. So f of a is the sine of 0, which is 0, and f prime of a is going to be the cosine of 0, which is 1. So our first order Taylor polynomial approximation of the sine function centered at 0 is 0 plus 1 times x minus 0, which is just the line y equals x. P1 of pi over 16 then is just pi over 16. We'll take a look now at our error estimate. We know that r sub 1 of x, the error in our first degree polynomial, is exactly equal to the second derivative at some value c over 2 factorial times x minus 0 squared. But we don't know what c is. However, we know that f double prime of x is going to be equal to the negative sign of x. Well, the absolute value then of f double prime of x is less than or equal to 1 for all x. That's the natural bound we have on the sine function. So this tells us then that r sub 1 of x must be less than or equal to 1, this is our m value, times the absolute value of x minus a, which is 0, raised to the second power, all divided by 2 factorial. So the error in our estimate of pi over 16 is less than or equal to the absolute value of pi over 16 squared divided by 2 factorial. So our error is less than or equal to pi over 256 times 2, which is 512. That's pi squared, actually. And that value is 0.01928. Let's look at what a calculator tells us the sine of pi over 16 is. The sine of pi over 16 is going to be equal to 0.195090322. Our estimate for the sine of pi over 16 was pi over 16. We saw that sine of pi over 16 was approximately pi over 16. Absolute value of sine of pi over 16 minus our estimate for pi over 16 is equal to 0.0012592, which is certainly less than the error bound we found, which was 0.01928. Wrapping up what we know, if we can bound the n plus first derivative of a function f on some interval between x and a with a number m, then we know that we can bound the error in the nth order Taylor polynomial so that that error is less than or equal to our m value times the absolute value of x minus a raised to the n plus first power all over n plus 1 factorial.